So we all want to build fast, reliable apps in the cloud, right? That's the goal. But what if I told you that the very features designed for reliability, the ones you lean on every day, are hiding a really dangerous flaw? Let's dig into this super common problem and its surprisingly elegant solution. I want you to imagine you're Timothy, a junior engineer. You come into work and this support ticket is waiting for you. I mean, your heart would just stop, right? You check the logs and they clearly show a single order-placed event was sent. So how in the world did a customer get charged twice? See, this isn't just some simple bug. It's a puzzle, and it's rooted in how modern cloud systems actually work.
Okay, so Timothy's senior colleague, Margaret, she sees this ticket and she knows exactly what's going on. This isn't a mistake in their code. Nope. It's a deliberate design choice in the infrastructure they rely on, and this is where we get to the absolute core of the problem: retries.
And this, right here, this reveals a fundamental trade-off in distributed systems. You know, the services we use all the time, Amazon's EventBridge, SQS, SNS, they are all built for insane levels of availability. Their number one priority is to never, ever lose a message. And to do that, they make a very specific promise. Your message will be delivered at least once.
And that is the catch, right there. At least once is a guarantee that sometimes, just to be 100% sure a message got through some network hiccup, the service is going to send it again. So get this, duplicate events aren't a bug. They're a feature of a highly available system.
And this is the big takeaway, the thing you have to understand. The responsibility suddenly shifts to us, the developers. We can't tell the cloud, hey, stop sending duplicates. It's not going to happen. We have to design our applications to expect them and handle them gracefully. The real problem was never the duplicate message. It was how our code reacted to it. So that brings us to this really core principle in computer science. It's absolutely essential for building safe systems like this. The whole concept is called idempotency, and it's the key to solving Timothy's double charging nightmare for good.
An idempotent operation is just one that you can run over and over and over, and you'll get the exact same result after the first time. The best way to think about it is like an elevator button. You can press it once, or you can mash that thing 10 times, but the elevator is still only coming once. Our payment function needs to act just like that elevator button.
So how do we do that? Well, as Margaret says, the solution is memory. The payment function just needs a way to remember, hey, have I already processed this specific order before it even tries to charge the card again? And this is where our junior engineer, Timothy, he comes up with an idea.
And you know, Timothy's logic here is totally sound. It's what pretty much any of us would think of first. Step 1, check a database table. Step 2, if the order ID isn't there, write it to the table. And step 3, charge the card. On paper, it seems absolutely perfect, but it's hiding a tiny, and I mean tiny, yet catastrophic flaw.
Okay, so let's break down exactly how this goes wrong. Imagine 2 of those duplicate events hit at the exact same millisecond. 2 functions spin up, they both race to the database at the same time, and they both see that the order ID is missing. So what happens next? They both write the ID to the database, and here's the kicker, they both charge the customer's card. Disaster.
And there it is. Margaret nails it. That tiny, tiny gap between reading from the database and writing to it creates what we call a race condition. It's a situation where everything depends on the timing of events you can't control. And in that race, the customer always loses. Okay, so if read then write is a no-go, what's the answer? Well, we need to find a way to combine that check and that write into one single unbreakable step. An atomic step. And this is where modern databases really come to the rescue. The tool for that job is something called a conditional write. It's a super powerful feature in databases like Amazon's DynamoDB. And this isn't a read then write 2-step dance. It's a single powerful command you send to the database that basically says, do this thing, but only if this other condition is true. And you can really see the difference side by side here. On the left, you've got that flawed approach with 2 separate steps and that dangerous little window for a race condition. But on the right, the atomic approach is a single locked operation. The database itself guarantees that even if 2 requests hit at the exact same microsecond, only one will ever succeed. It's impossible for both to win. That phrase right there, only if it does not already exist, that is everything. We're not asking the database a question and then deciding what to do. No. We are giving the database a command with a non-negotiable condition attached. The database handles the whole thing.
the check and the write, atomically. And that closes the race condition window completely. Okay, but what about that second function, the one that lost the race? Well, DynamoDB just rejects its write attempt and sends back a very specific error, a conditional check failed exception. And our code is written to expect this. It catches that specific error, knows, this is just a harmless duplicate, and simply stops. No card gets charged. It's this weird situation where a failure is actually a complete success for our system. All right, so now Timothy, who's a pretty sharp engineer, starts thinking ahead. We've solved the safety problem, which is awesome, but have we accidentally created a new one? A problem with cost and just endless data? And he asks a great question. If we're storing a record of every single transaction, isn't this table just going to grow forever? Won't it become bloated, slow, and crazy expensive? It's a really valid concern. And again, there's this really elegant feature that solves this problem perfectly. It's called time to live, or TTL. The thing is, we don't need to remember these transactions forever. We just need to remember them long enough to outlast any possible network retries. TTL lets us put an expiration date on our data. In this case, Margaret figures, 30 days is more than enough time to catch any weird network retries or stray duplicates. So every record that gets written to this idempotency table gets an automatic delete by date. After 30 days, DynamoDB's TTL process just swoops in and cleans it up. And the best part? That cleanup is totally, completely free. Okay, so let's just recap the whole solution piece by piece. We've got a fast, event-driven system. It's using at least once delivery for reliability. We make it safe using an idempotency key. We implement that with an atomic conditional write, so race conditions are impossible, and we keep the whole thing cheap and clean with TTL. And that is the transformation. By really understanding the guarantees of his tools and then designing for them, Timothy took a system that was fast but also kind of fragile, and he turned it into one that isn't just reliable, it's mathematically safe from one of the sneakiest problems in distributed systems. And that really just leaves one last question, a question for you to think about. In your own work, you've probably built services that are fast and decoupled. We all have. But have you really accounted for that at least once guarantee? Are your systems truly 100% safe from duplicates?